PACM has this tradition of having a distinguished lecture and goes back a number of years. And we have had wonderful speakers. And this year we have our own Ingrid, because all of you know, Ingrid has many claims to fame. President of the IMU, past president of IMU, great luminary in wavelets and applied mathematics, applied harmonic analysis, and chief among them was the fact that she was in PACM, a great leader of PACM, director at some point, co-director, whatever, I don't know exactly the shaper of PACM, we can say. And I don't want to go on forever about the many achievements and the great, but one of the important things about Ingrid at PACM was that she set an example of atmosphere, encouraging people, attracting people, making people feel excited and welcome, and we only hope to emulate that. So I'm very happy to present Ingrid for tonight.
Wow, thank you. Well, thank you very much for that introduction, and I immediately have to say that if I helped shape PACM, I'm very proud of that. But certainly, I'm not the only one. I mean, there are other people here who did certainly as much, if not more. And I can also tell you that from what I've seen of the students, the tradition of being enthusiastic and talking to everybody about everything everybody is enthusiastic about continues, and so that's great. Okay, so this is a lecture which for a broad public, so there will be mostly pictures and no equations. But I had a colleague at Bell Labs, Leo Flato, who said, a picture is worth 1,000 words, he says, but only if you have the 1,000 words. So I can guarantee you that for all of these pictures, I have the thousands of words. And so I'm happy to tell you more about them and to give you references afterwards or separately. Okay, so I want to tell you tonight about something that a long-term project, actually it's a whole series of projects on which I started when I was still at Princeton, which is the development and use of image analysis tools and the mathematics underlying them for aims to help art historians and art conservators. And well, I made a facetious little title where you see these two hands, which are very famous, and you could view them in any direction you want. I mean, it's something actually where both communities, I think, have enjoyed the collaboration very much. So in the second half of this presentation, I will talk about my own work in collaboration with the North Carolina Museum of Art, and it will feature students and collaborators of mine, as well as curators and conservators at the museum, in the North Carolina Museum of Art, and a Dutch artist. But before I start, I'd like to already tell you about two different examples of mathematics helping art historians and art conservators, which I think are two beautiful examples that I like to use in my teaching now. The first one is by Massimo Fornazier, who actually was a postdoc with me here at PACM, but the work I'm going to talk about is work that he did earlier when he was still a graduate student. He worked on helping to reconstruct the frescoes of the Eremitani church in Padua, in Italy. So this church was near the end of the Second World War, was bombed by the Allied troops by mistake. And after this, the church had been very famous for beautiful frescoes by Mantegna and other painters. And sorry,
she's adjusting the lighting.
Oh, I'm sorry. I've learned how to do this, I just forgot. So these frescoes were completely destroyed. Here was a mock-up of what they looked like. Actually, the bottom fresco here is not a mock-up. The bottom one is the only one that was preserved. And it's preserved because it had been removed from the church because it had some water damage, and they were trying to repair it. And so that was the one that was in safety elsewhere. But all the others were reduced to this kind of rubble. So after the bombardment, art conservators collected boxes and boxes and boxes of this rubble. And every so often they would, over the ensuing decades, think that if they had some time, try to see whether they could save anything. But really, there was not much that they achieved. But in the early 90s, they thought maybe with computational techniques, something might be possible now. And so all the fragments were cleaned, consolidated, catalogued. Actually, some fragments came out of the woodwork because when there was a whole press propaganda, press description of this project, and so people would come and say, you know, we have this fragment. My grandfather, I'm very ashamed, took this as a souvenir from the church, but now that you're going to do something with it, please take it back. I mean, but well, those were just a few. But so they were all digitized on a collection of CD-ROMs. And here you see an example of some of the data they had. Here are a few of the fragments that they actually had pieced together over the years. These were, I think, all the ones they had. And they were numbered on the back. And this information was made available to anybody who wanted to propose a solution to do something with these. So these were all fragments that had a few square centimeters. They had no context. I mean, if you see here, I mean, you can see there's something on there, but it's hard to know what exactly you're seeing because you only have a few features. And of course, not only do you not know where they were on the fresco, but you also don't know in what rotation they were sitting. They did have, as I've shown you in the mock-up, very high quality black and white pictures, which they could parallax correct and so on. So they had what is like the cover of a puzzle box, I mean, but in black and white, where you could put the pieces, but they had no idea where to put the pieces. Not only that, but as you can see, they knew they had more than 500 meters squared worth of fresco, and they knew they had at most something like 75 meters squared of puzzle pieces, so that they had lost almost 90% of the puzzle. So you have an enormous box, you don't know where the pieces go, and you only have 10%. And so it was a hopeless task. But Massimo came up with a method that was implemented, and you'll later see the results. So these images were digitized. A digital image consists of a whole lot of points on a grid which you give numerical values. I mean, numerical values that tell you if it's a black and white picture, what the gray value is. If it's an 8-bit image, then you have numbers going from 0 for all black to 255 for all white. And you have these 254 different shades of gray in between, which we have many more. Others only have 50, but we have 254 in image processing. And once you have digitized your image, you have all these numbers. And now that you have this numerical representation, you can do all kinds of operations with these images and do meaningful things to the images by computation. Now, if you might think, well, if I have two images to decide whether they're identical, all I do is I compare the numbers. And if the numbers are identical or close, then I'm fine. Well, not quite, because you could have shifted your image slightly, and the pixels that you get would correspond to a slightly different area, and the numbers would look different. But not only that, I mean, you also have that the image could well be rotated, as it is in our case. And here I have two arrays that correspond to numbers of around the same point in the painting, actually, but one is rotated and the numbers are completely different. So how are you going to deal with that? I mean, if you don't know exactly where things are situated. And so Massimo came up with the idea of using circular harmonics. So what are circular harmonics? I mean, if you have a little disk area of image worth, and that's what eventually was done on all the little pieces of plaster where there was a feature. I mean, if it was uniform yellow, you couldn't do anything. But if there was a feature, then they would take the disk, the biggest disk that they could inscribe, that was all fresco, and they would decompose it in these circular harmonics, which look like these functions. And they are very, very special. They are building blocks, meaning that if you decompose an image on a disk into these building blocks, then you decompose it and you have a linear combination with coefficients. Then, like here, I mean, here we take the image at the bottom right and I show you how by adding, every time I've added one of the building blocks that was shown here, but with the right coefficient, how that builds up the whole image. And if you rotate the image, then we know that it's the rotated image. We don't have to decompose that rotated version into and so on. We know exactly how that is transformed under the rotation. Depending on the angle, you know that you have to multiply the coefficients with very special coefficients given by very special weights given by the rotation angle. And so you immediately know from one decomposition what all these others are going to be. So you can compute, and that was what done, for each of these circular images, the decomposition was computed, and then that was going to be tried out in rotated versions, because the rotation was so simple to carry out, with different placements on the image. So what they did actually, the whole experiment was also a sociological experiment, something in which the whole community worked. Because we're talking now, I mean, we're talking about the computational resources of more than 15 years ago. I mean, now supercomputers then probably were about as performant as your iPhone now. So what was done was that this database was set up, and Computational Studio was set up in the center of Padua, and volunteers would come. And they would come and take out of the catalog, they would extract a fragment, and then that fragment would be searched in the catalog, and they would then inspect what the research results were. So here is an example of fragments that actually already belong together. The catalog element is taken, and then the top 3 results are displayed. And the human operator would then decide which of the 3 was the best match. I mean, in most cases, the best match was the true match. But in some cases, I mean, here, for instance, you do see that there is a possibility of it being part of the of some floral decoration, or part of the ridges on a column. And it was clear that it was the hair of this person that was the true one. But the human operator would decide that for 2 reasons. One was that in the cases where the top match was not the exact match, one of the other 2 matches was almost always the correct one, and a human operator could easily see that. The second was that the art historians really liked much more the idea of having a human in the circuit. So it was a good sociological thing to do. It also made it much easier to compute. I mean, it's easier to design an algorithm that will give you the best results among the top 3 than one that always has it 100% right. And these days we probably could do it, but I'm telling you, I mean, this was over 15 years ago. So over 80,000 fragments had to be allocated like that. They were all very small. Only about 10% of the whole area was known. In here, I mean, and they were all the ones that had features were found. So here is a fresco where you see all the features as they are. So try imagining doing that as by hand in a puzzle. Here's another one. And you might ask, well, how much good does that do you? Art, if you have this amount of information, then art conservators can actually reconstruct faithfully the color information on the whole image. I mean, because even if you have a modest information, like imagine here, you have information about the color of the marble stone, on the color of the lance, of the skin color of the soldier, the sandal, of the decoration on his leg, the inside of his shield. I mean, you have enough information that you can propagate, and that is actually exactly how you can art conservators do it. They take what they have and they propagate a bit more and a bit more and a bit more and so on, and that's how they fill it in. Here again, you could imagine filling in the information, or here. If you have this in black and white and you have this color information, then you can propagate it to get this. And so in the church, this is a picture that was taken during the restoration of the fresco. This is a view of the fresco we saw earlier in black and white, the way it's now shown in the restored church. So the decisions, I mean, for art, cultural, historical reasons were taken. They decided that on some areas they would just show the real fragments embedded in the black and white. In some they would paint in slightly more pastel versions of the colors, what it had been before. But you can also see on computer screens the fully colored inversion. These colored inversions here were computed also by algorithms that Massimo provided, in which this propagating, taking the information and taking it a little further and a little further was done mathematically rather than by doing it with paint. And actually that whole algorithm is called in-painting, and that is based on what the conservators, it's a term that was coined by conservators. They were painting in holes, defects, I mean paint losses on paintings in museums. And that term was taken over by Guillermo Sapiro when he developed these algorithms to propagate color through. Okay, so this is a project that got a lot of press at the time. There's a beautiful coffee table book on the whole thing, and Massimo deservedly got a very big prize from the European community for this. Let me tell you about the second project. So it's a project by Rick Johnson, who is an electrical engineer. I mean, he's now retired, but he was then at the University of Cornell. His main study was not images, but audio. But in about 10 years ago, he went on sabbatical to Europe, and he always had been very, very interested in art. He had a minor in art history, and he, via common friends, got introduced to the conservators of the Van Gogh Museum in Amsterdam. And he was very impressed by everything that was going on behind the scenes. And he said, look, you guys use science in so many ways. Use infrared, ultraviolet, use chemical analysis, you use many different ways, I mean, other modalities. He says, but I don't see you use any image analysis. And I said, well, image analysis, we are highly trained visual experts, and they are, there's no question about it. I mean, you would be amazed at the things that by studying these paintings very carefully they have deduced. For instance, they know that Van Gogh was not careful with his finished paintings. He didn't let them completely dry. He would stack them against each other, and so on some of them you see impression of the back of the canvas from a previous one. And then he realized that that might not be so good, so he started putting some newspaper print in between. So some of them have letters of the newspaper on them. So I mean, these people are incredibly meticulous in looking at these paintings. So they said, why would we do image analysis? He says, well, you might be surprised. I mean, there's a lot that image analysis does these days that is not something our eye does easily. And so he saw it as a challenge, and they made it possible for him to organize a workshop where he would bring people who were working on image analysis. And the lure he had for them, and that the Van Gogh Museum provided to them, was that he would make available high-resolution versions of pictures, digital pictures of the Van Gogh paintings. Now, museums have become a little bit more open about that recently, but at that time, museums were very, very close-fisted about high-resolution data on anything in their collections. I mean, this was their intellectual property, and they were not letting this anybody. I mean, so in order to get access to the data, I had to kind of sign my soul away in case it ever leaked. But, well, they have never leaked, and I'm still in possession of my soul. But, so Rick Johnson, so we did a number of different projects. But at the time, the Van Gogh Museum was also in a process of making what they call a catalogue raisonné of theirs. So what that means is that you make an immense book in which about each painting you make a summary or you refer to everything that's scholarly known about that painting. So everything. I mean, the correspondence with Theo van Gogh and so on, everything that had been concluded. And one of the things that curators and conservators want to know about a painting when they characterize a painting is the weave of the painting, the canvas. They want to characterize what the canvas is. And you can see that canvas very clearly, for instance, on this X-ray. You see that's an X-ray because you see the nails very clearly. And I mean, these metal nails show up more clearly. So, and you see the threads, horizontal and vertical threads. Now, you might wonder, why should I see canvas on X-ray? First of all, why can't I just see the canvas by turning the painting over and looking at the canvas on the back? That's because many canvases, and in particular the canvases that Van Gogh used, which were not cheap canvases, but also not the most expensive you could ever get, are not stable over a long period of time. All the solvents that are used in the paint that you apply to them to make a painting gradually break down the canvas, and those threads become very, very friable and disappear. And that makes the painting much less stable, of course, if there's no support, if it only hangs together by how the paint. So these paintings have been relined, which is a very standard thing to do with painting. What is done is that a much more solid fabric is applied to the back. I mean, it's glued, and in Van Gogh's case, as was often the case then, ironed on. So, so at the back you don't see the original canvas. Even at the front, where canvas might have been seen as a relief, you don't see it anymore because of the ironing. However, you do see it in the X-rays, not because the canvas shows up, because threads are not something that shows up in an X-ray, but because of the way these canvases were treated prior to painting. I mean, in order to prepare a canvas for painting, if you don't want it to absorb your costly paints too much, you first put a primer on. So, and that primer layer, a white primer layer, contains, in many cases, and certainly in the 19th century, contains lead. And when you have valleys and mountains, in the valleys you have a little bit more than you have on the mountains between the threads, and so you have this thicker, thinner lead-holding paint, and of course that shows up on X-rays, and that's what you see. So here you see the X-ray, and then it's negative. And so what in a catalogue raisonné, what the curators would do, they would look at it under a microscope, and they would have a little inch thing next to it, and they would count so many threads per inch here and so many threads per inch on. And they would do that in 6 places until their eyes glazed over, and that would be the characterization of that canvas in horizontal and vertical direction. And so when we learned of this, I mean, and you might think horizontal and vertical, well, there are deviations from horizontal and vertical, which is very obvious in this painting. I mean, it's not completely flat. This is an extreme case. And of course, the canvas, once primed, is put over a stretcher and really tended nicely. But the priming of the canvas happens before it's put on the stretcher, typically. And that freezes the slight waviness of the... After that, you cannot really correct for that anymore. And that's why you see that waviness, even though this was a nicely flat and canvas stretched over its stretcher. So when we heard about this, we said that is something that we must be able to do easily with image processing. And indeed, Rick Johnson did that together with another Johnson from Rice University who was in image analysis. And what they did was they would take little patches and look at a local Fourier transform. And they would look at the direction in which the coefficients, which you had the highest frequency, because that was the direction in which we were perpendicular to all these lines. And so you would get the weave and the warp direction. And they would display the information, because they now had this all over the painting, in a very visual way. They would, for both the horizontal and the vertical thing, they would make 2 images. And I'm only showing you 2 of the 4 that result. They could, for each of them, show the frequency, namely how many threads in that dominant direction. And then they could show also the deviation of the angle from the horizontal or the vertical. And here you see the deviation from the angle, and you see one of the deviation of the angle in one direction, and the other is the frequency in the other direction. And because they had the information everywhere on the whole canvas, not just in 6 spotty places, something became apparent that nobody had expected, namely that you now had really a fingerprint of the canvas. These are 2 canvases that were painted on subsequent days by Van Gogh, and you see that, as he often did, he had bought a big piece of canvas, and he cut it into pieces, and you see the 2 subsequent pieces here, because the fingerprint identifies it clearly. And these 6 paintings have been, I mean, they now are known to be what they call roll mates. They came from the same roll of fabric, because in one of the 2 fingerprints, they've been pieced together like this. So this places them in one direction, and this places them in the other direction. And in fact, there's a painting, this is a painting from the Arles period. There was a painting by Gauguin that also is a roll mate of these, because they were sharing a house for a couple of months. This technique has since been used on a number of different paintings, and one of these is it has been used to reattribute a painting by Velázquez that had been deattributed. It was not one of the master's best days, and so it was not up to the same high quality as some of the other roll mates. But before it was found that it was a roll mate, they thought it might have been by one of his students, and they didn't believe that he was sharing his most costly canvas with his students, and so now it has been reattributed. So interesting studies, and these, I like these 2 examples because they're interesting and so on, and they're very, by college standards, very elementary mathematics, so they're nice examples to use in teaching. So Rick Johnson got me into these projects on art, using image analysis for art. And so when I started work on the first workshop, the first project we had been given by the Van Gogh Museum was to try to distinguish in the high-resolution images of paintings whether things were of the same style or similar styles, and distinguishing originals from copies. But the most interesting thing that happened with that is that, so it was an interesting project, but of all the projects on which I worked on, it was actually one of the ones that I think is among the least appealing, this originals and copies, even though it made a NOVA program, and you can still find it on internet, a little snippet of television where they show this and so on. What was really interesting is that when I gave a talk about it, people said, oh my God, if you can do this, maybe you can help me with that. And so more and more interesting projects came our way. And the first one of those was what I like to call, and art historians don't like it when I say this, Lady 6 millimeters under. So this is a project for which I was approached by Joris Dick. Joris Dick and Koen Janssen are 2 material scientists. Joris Dick has a degree also in art history, who made the front cover of the Journal of Analytical Chemistry with an investigation of a painting by Van Gogh that's illustrated here. So the painting that they examined is called A Patch of Grass, een polletje gras. It's from his Paris period, and it's a study of grass in bloom. And if you turn it on its side and you take an X-ray, then you see that there's something else underneath. Now, that's not surprising. I mean, about 30% of Van Gogh's paintings have something else underneath, because canvas wasn't cheap and he was poor. And so when he made a study and he felt he had learned everything he could out of that study, he would apply a new layer of primer and use it again. So, but this painting was particularly interesting to people because it shows a portrait of a peasant, like Van Gogh painted maybe a few hundred during his Nuenen period, the period just before he moved to Paris to live with his brother. And, but there's a letter from Vincent to Theo van Gogh, his brother, in Paris, that survives, as does most of the correspondence between the two brothers, in which he describes that he's sending a painting to him. He says, I've been trying for, as you know, for many weeks to capture with a very dark palette the impression of color in dark circumstances. And I'm sending you a painting in which I think I really particularly well achieved what I wanted to do. And the painting that he describes was never found, but that letter was. And this painting, this portrait, is underneath a painting that he painted in the Paris period. So this canvas was in Paris. Now it's not unlikely at all that once Van Gogh came to Paris, met the Impressionists, changed his style completely, he did not think as highly anymore of a painting that he'd earlier described as particularly particularly successful in something he wanted to do. So it's not unlikely that he would use it to repaint over it. And so people believe that that was that painting. So they were interested in finding a little bit more that's where Koen Janssen and Joris Dick came in. There's a technique called X-ray fluorescence, where you, which is now used and has been used for many more paintings since then. And often if you read about new features that have been discovered in paintings through X-ray techniques and so on, or a new master that is discovered underneath something less important, very often these techniques are now used, so it become much more, but this was the first painting on which this was used. And so very small areas get illuminated with a high energy X-ray beam, and which excites the electrons, which then fall back in two steps. And the second step is between two bound states of the atom in question. And so that frequency characterizes the element that you're watching, that you're looking at. So that what they did is they bombarded little pixel by little pixel with the X-ray. They would measure the whole spectrum and the intensity of the different lines, and they could then correlate to what elements were the different lines. And so here you see for that painting what they saw in antimony, which was an element used in a compound of Naples yellow that Van Gogh used, and arsine, which was used in his vermilion. I have here also, no, this is, so this is what they had measured. And they had used this information to colorize the painting, and this was what they got out and what you saw in the Journal of Analytical Chemistry. And Joris Dick said, look, this is what we could do with our data, but you guys, you know image analysis, maybe you can do more with the same data than we could. And for instance, he says there are all these black spots, which are spots where we don't have data because there was impasto on the top painting, and so the X-rays didn't penetrate enough, so we don't have data. Maybe you can do something. And I said, sure. But it turned out there was more that needed to be done. Because when we looked at the data, and I then asked Joris Dick, he says, oh yes, I'd forgotten. The data was full of artifacts of this type. I mean, so this was clearly one black spot that has been kind of zigzagged apart into two. The reason for that was that, well, this was the first painting on which this was ever done. Museums don't have high energy X-ray beams lying around like that. To get such a beam, they had gotten money to cover the insurance to transport this painting from a museum to a hospital in Amsterdam that had high energy X-ray sources in order to fabricate short-lived radioactive elements used for medical tests. And when there's an apparatus like that, usually it's designed in such a way that when the beam is not used for its day job, it can be used in a different direction for physics experiments that help pay for this costly experiment, for this costly apparatus. So they had gotten time on the beam, and the painting had been put on a little sled, and would move. The beam was always in the same place. The thing would move by pixel after pixel for the next measurement. And of course, as soon as the beam was needed for its real job, the whole thing had to stop, and they had to use the beam, and then the beam would come back and they would proceed again. But they had made a mistake in synchronization. And I mean, this was a one-shot thing. There was no question of coming back with the painting again. I mean, the money for the insurance which was many thousands of dollars, was gone. So these were the data. And so in order to get the image that here, Joris Dick had by hand corrected a little bit, but he said it's probable that we have these kind of breaks everywhere. And so what we did was we first cleaned up, we found a variational algorithm to go through the data in several goes in order to find where the breaks were and to minimize the variation by readjusting. So that was the first thing, which was already a nice task and not a task that I ever would have expected to need for image. So then next we did the in-painting. So we put a mask on all the black stuff and we used in-painting techniques to fill that in. The marks of the very long grass things, we also masked, and we used a different in-painting technique to fill those in. And then we still had some problem with the eye. And we asked the conservators, we said, with the eye, that's very special. He says, oh, use the other eye. We do that all the time. And so we did that too. And so here is what you get. Now, after that, and well, here to show you how delicate this in-painting is, I show you a place where you have this black spot and then how it gets in-painted really nicely. I mean, so this, I mean, they had not only corrected for the breaks, which we had done, and we had done in-painting, which they hadn't been able to do. They also had gotten color information. Now, I showed you we had red from the Arsene. We had Naples yellow, which gave an impression of light. It was the only light color on his palette. But we're missing all the earth colors, and they were not in the spectrum. I mean, they hadn't looked at a wide enough spectrum. They didn't have those data. But what we found was that when you looked at all the portraits that Van Gogh painted during this period, some of them have very high contrast, some very little contrast. But if you separated contrast from color, chromance, which is something that most people are not well trained to do, and even there was a much greater uniformity in the chromance. I mean, separating it from the contrast then. And so we could use what we had in order to extrapolate the remainder. And doing that, we got to this version, which really brought her much more to life. So this was something for which I had presented, and which when I moved to Duke, the conservators at the museum in Duke had heard of. And so they were eager to actually start talking about possible projects. And the first project we talked about is a project that is actually, we have some preliminary results, but we will do more. And so I just mentioned this in passing, is about a very, very famous altarpiece by Giotto, which had been separated, like many of these altarpieces in the 19th century, but had been reunited through the collecting efforts of the North Carolina Museum of Art, and which has been exposed together since. And art historians feel there is a difference in painterly quality and in hand between the different paintings, and they wanted us to see what our methods would find. And we have some, as I said, preliminary methods, but we are still working on it. So I want to tell you more about a different project, about a less famous altarpiece, also from the 14th century, that is also from Italy. That's also quite a bit smaller, of which the North Carolina Museum of Art has 3 panels. 3 more are in the Metropolitan Museum of Art, and they are on display still. So one is in the Museum of in Portland, in Oregon. One is in Chicago, the Institute for Fine Arts. And the conservator told me that he had long hoped to bring them all together, because they're all in North American museums, and so it would be much easier to reunite them than if you also had to bring in European museums for a joint exhibit, because they had not been together for the last 150 years. He says the other museums are not as enthusiastic, he says, because there's a problem, we are missing a panel anyway. So this panel, this altarpiece had been cut into different panels in the 19th century, when many of them were broken up because the churches needed money, and these paintings were becoming valuable because collectors were collecting them. And so they had sold the individual pieces as artwork and repaired the church with the money that brought up. And the 9th panel here is lost from the records, so there is no description of it, and it must have existed because the altarpiece doesn't make sense otherwise. But and I then said, well, but you know, maybe something. This reminded me of an artist I'd worked with, Charlotte Kaspers, who I know very well. We had collaborated because remember there was this trying to distinguish originals from copies. And the Van Gogh Museum actually had hired somebody to make a copy to challenge us. And that was who they had hired. She is a fantastic artist, but she's also trained as an art historian and a conservator. And she, museums often ask her to make reconstructions of art. Here she has been commissioned to paint a detail of the altarpiece in Ghent. That is on display now. She painted the same piece 3 times, and she stopped at different stages, and so that she could illustrate to people all the different layers that would go into making such a painting. Here's the same principle for something that she did for a museum in Rotterdam, where she stopped after about a 1/4 inch every time. With every layer. So you see the naked piece of wood everywhere, then a piece of glue, 2 layers of glue, 3 layers, and so on. Here, the first layer of gesso, and so on. I mean, she's already halfway before she even starts drawing on the thing. And then you have drawing, fixing the drawing, and so on. And so paint only comes at the very end. I mean, we're months into the thing already. So I told them about her. She and this was when Nova challenged the copy which we had detected, and I actually had brought her to Princeton, where she painted, because for validation we asked her to make a series of original paintings and copies of those original paintings, because she's trained in the art of copying, I mean, which is a different thing from freehand painting, and we wanted to not be distracted by the hand of the artist. So we had the same hand, but in 2 different actions. Here you see her in the painting, in the act of copying, where she's holding her hand and going with the brush over it. So I have a whole collection of portraits of Tchotchkes in my house. Yeah, she was in the basement of our house. You see the drum set of my son, who was still living at home then. She came actually a few years ago when we did a project at North Carolina Museum of Art. She made copies of birds of North Carolina, where for one set of these we know which the original and the copy is. Green is original, blue, red is copy. For the others we don't even know. And for those among you who have heard about or worked on machine learning, in machine learning we always know the ground truth and we say we didn't use it and so on. I mean, art historians don't buy into that. So here we really don't know. I mean, the information has been consigned under sealed envelope in the art history department, and we don't know. In fact, this year we had a student work on the first, I mean, and so on, and in this data set, even though we held a little party where we made people vote and the majority of people got it wrong, her algorithms got it right. And we uploaded a little YouTube video about it. But anyway, so that's why we had worked with her, and I said, maybe she can help. Now, of course, it's very different to copy a painting that's in front of you and reconstruct one that you've never seen. But it's not as strange as you think, because although we don't know what was there, experts very well know what the scene is that should be there. Because this is like a comic book. It's a very codified thing. It's the life of John the Evangelist. and they know what should be there. It's the baptism of the guy who is incredulous here and who's challenging him to drink some poison that has been used to execute two criminals first. They're lying there on the ground, you see, it was really poison, they're dead. And after John drinks it and doesn't fall dead, the man is overcome and asks to be baptized. And so that's the last scene. And so a scene could be made that was in the same style and that was consistent with the others. Now, if ever that ninth panel is found, it's clear that it won't look the same. But what the goal was to make a panel that would look like it would not have been surprising in the 14th century if it had, by miracle, taken the place of the original. So here you see her, she's applied the bolus, she's gilding, she's polishing the gold. Punches were made, she's punching the gold. And this is a little detail of that scene. Now, the fact that there was now this ninth panel adds a whole dimension to the whole project, because a movie was made, a documentary of how she made this new painting, so people will see how the traditional things worked. In her work, she followed a manual that we have, a 14th century manual of how these paintings had to be made, so she really followed all the steps. And so it will give a fantastic impression, and when this exhibit will happen, which actually is going to take place, the other museums are now interested, and it's going to start in September in the museum in North Carolina, in Raleigh. They will get a wonderful impression of what these paintings looked like when they were new. And when we were planning the exhibit, about 6 months ago, when we first started thinking about that, they said, but this is terrible, because we can't hang it next to the other ones. Because everybody will look at this new, shiny, beautiful one, this bright one, this highly colored one, and the others will look dull next to it. And it's the only one that's not original. I mean, the other ones are really the treasure. And so we said, well, but we can help. Image processing can always help. What we do is we can study the old paintings, and we can, with that information, virtually age the new one, because they didn't want to physically age it. For two reasons. First of all, they wanted to show the new one and what it is like when it's new. But also, museums are not in the business of making artifacts, even if they're documented, that could be mistaken for fraudulent things. I mean, they just don't want to touch that at all. So they were not going to age this thing. So, but we can virtually age it, and then make a high-resolution print that can be displayed. I mean, that will clearly be a print on very nice paper, but on paper compared to the nice panels. And then separately, the new painting will be shown. And with a documentary of how it was made, and with a cabinet that shows all the materials and the pigments and the punches and so on. And there will be even a workshop organized to do the techniques. And we can do that. But we can also, if we study all that, we can use that same color remapping and so on to rejuvenate the old panels. So that's what we're doing right now. And so there will be, apart from the contrast between the old and the new panels, there will be also a projection of the old versions, details of the old versions that move and become virtually rejuvenated. And, well, why was I so confident that we could do this? Because we have done something similar before. In the Ghent Altarpiece, the same one that I was talking about earlier, and by the way, if any of you have seen the movie Monuments Man, that's the painting that everybody is chasing for. This is this very famous, very iconic, and very important painting that was abducted at the end of the war and that was brought back to Belgium. So this is that fantastic, glorious altarpiece. It's a polyptych. If you close it, then you have these many different scenes here. In the scene of the Annunciation, at the back of Mary there's a book. Well, there's the painting of a book. And now we're talking about something that's about 3 inches high, maybe. And in this 3 inches high display, well, it looks like a medieval book. And I cannot read a letter of this, but then I can't read them in books in museums either. But paleographers who can read the books in museums couldn't read this either. And so people said, well, it's obvious. I mean, it's a painting of a book. It's not a book. I mean, he was just doing some squiggles to give the impression. And already it's much more detailed than most people would draw a squiggle. But and others said, well, you know, Van Eyck is really, really a perfectionist. And the reason that it was still a debate was that it's very hard for people to actually think away those cracks. I mean, our eyes can do fantastic things. You've all seen this illusions. I mean, you know this image of the three Pac-Men, and we all see that triangle there. I mean, so our eye can do fantastic things, but we are not good at thinking away cracks like that. Even experts are not good at it, because the browns are the same, the things are in the same direction, and so on. And so I said, well, we can try to, first of all, automatically find which pixels are cracks and not paint, and then try to in-paint. Now, if I'd known how hard it was, I might not have spoken so quickly. But it turned out it was possible, but it became a good portion of the PhD thesis of an electrical engineer in Belgium. And we did do the in-painting. Now, for in-painting, we only used the fact that this was painted. We didn't use the fact of this looks like over there and so on. We really, honestly, only did in-painting. And when we were done, I said, well, what a lot of good that does to us. I mean, we can't read anything more, and we couldn't. But the paleographers started recognizing things, and they started saying, oh my God, look, this is an A, it's not a piece of a W, and so on. And so they recognized 12 groups of words that are, without any doubt, they established for all their colleagues that this is a page from a book by Thomas of Aquinas, copied in the early 14th century. It's an older book, but on the Annunciation. I mean, and so they were really excited because it's in an Annunciation scene. And so now that we know that this has been established, we can use character recognition in order to recognize even more text, because they'd like to identify exactly which copy, depending on how things are organized and so on the page. But that's a different story. But so we can do cracks. So because we could do cracks, I said, bring us your X-rays on the Gissi Altarpiece. We'll get the cracks out, and we'll do that in painting. And we're doing all that as I'm speaking. But we have work-study students working on this. And so on the X-rays, you see the cracks very vividly. And I said, what's this nonsense on your X-rays? I mean, these horizontal and vertical things. Doesn't that bother you? And I said, yes, it's the cradle. It's a cradle. Well, when these paintings were bought up by collectors to hang in their collections, in their galleries or in their homes, they were all very thick paintings on wooden boards, these altarpieces. All these paintings on wooden board were very thick. And as a result, they kind of worked as wood also. Some of them also had damage. I mean, so like here you see some worm damage at the back of the Gissi Altarpiece. And they tried to remove the decayed wood or the damaged wood. But mostly they wanted to make these things thinner so that they could make them completely flat instead of this undulating thing on their walls. And then in order to give them structural integrity again, because they had gone from being an inch thick to being just a few millimeters thick, they put a hardwood cradle on the back with slats in one direction and things tunneling through in the other direction. And that gave them. Okay, all that was before they realized that taking X-rays of their paintings was very instructive for art conservators. And once you have that hardwood, all you see on your X-rays is hardwood. I mean, and so many people say it's impossible to study the painterly content in these paintings because I said, well, for our crack study we don't care, but I guess for other reasons you might prefer not to have these cradles. I said, how come I've never seen this? He said, well, because before we publish something in a journal, we spend hours and hours removing that with Photoshop. And it's not easy because it's not exactly horizontal, not exactly vertical. I mean, the grays are not uniform, So I said, well, maybe we can do that. We can make an algorithm to do that with image processing. But it didn't seem like, I mean, we didn't need it for our project. And so I said, then maybe for a couple of paintings, doing it by hand is not so bad. I said, but there are more people who have such paintings. I said, yeah, well. And then a year later, I was at the Prado, and I talked with Laura Alba, who's their imaging head conservator. And I said, in North Carolina, I told me that I had this problem with the cradle. Do you have that too? And she says, do I have that too? She says, and she opens drawers and she shows me everything was cradled. And so I said, so would you be interested? Yes, she said, very, very, very interested. So we, again, at first I thought it's just a question of finding the location, which isn't hard, and then removing the gray values and so on. No, because it's more complicated, because this is wood, all this is wood. So you have, in many of these cradle things, you have wood structure. And they like to see the wood structure of the cradle removed, but not the wood of the panel, because the panel is wood as well. So then it became a much more challenging and very interesting machine learning problem, because it meant that you had to study in order to find what the wood grain was in uncradled, and the superposition of the two wood grains in cradled, and distinguish the two so that you could subtract one but not the other. And I have a graduate student who succeeded in doing that, and that's going to be part of her thesis. So our algorithm does, I mean, here you see two comparisons for a piece of, you see, this is what the expert, the Photoshop expert among the art conservators in the North Carolina Museum does. And you see, although she adjusts the gray level, but not as well as we do, the wood grain is not removed. And the wood grain makes it possible to then examine details in the brushwork much better. So I have a couple of examples. Here is the painting that was used on the poster. It's cradled, I mean, like all these paintings on panel. And here is what our algorithm does. So you can see how it becomes all of a sudden possible to look at much more detail in the brushwork. Again, because it's very hard to think things away, even for the experts. Here's another one by Van Orlé, cradled. And here you see blow-ups in the cradle that show you the wood grain in both the panel and so here is from that painting here at the bottom of the fabric, blown up, cradled and uncradled. And so, and okay, so what we hope and what we have done in the meantime is we had the algorithm. So then we wanted to develop it, because having an algorithm that works in MATLAB or even in C++, which was on this version, is just as well as not having anything as far as art conservators are concerned. I mean, they don't have MATLAB, they don't want MATLAB, they're not going to learn MATLAB. I mean, and I understand. But so what we did is we got a grant. I was actually really thrilled when we got a grant. I asked a grant from an art foundation, and I said, look, we can do this and so on, but we need to make this into a wrapper with Photoshop so that people can use it who are Photoshop users. And I asked for a student to supervise the whole, making the code robust and then porting it and so on, and then hiring people outside to do the Photoshop stuff. And when I got the award letter, it said this was one of the most intriguing and interesting proposals they had got. They were very happy to fund it. He said it also led to one of the most lively board meetings in living memory, he said. So I think they must have had a fight. I mean, some people must have said, our good money, spending it on that, are you crazy? I mean, others said, this is the future. I mean, anyway, we got the money, we did it. We've made it available in open source. The idea being that sooner or later people are going to want to do things with it that we did not foresee. We don't expect them to do things to the C++ or the MATLAB program, but we are providing everything and documenting it and giving the articles and so on. We're telling them, if you take this to local applied math or electrical engineering groups or image processing groups, they may be interested in helping you and working with you to do this. And we hope that this will spur more of these collaborations, because these are very unusual problems, different problems than what we get from other applications. And it's fun to work on these. It's much more fun to work on these than on, heaven forbid, Lena. I mean, and so we called it Platypus because we were looking for a good name for it. I mean, the software developer, the Photoshop developers told us you need a name for it. We said, well, virtual cradle removal, and they said, oh, this is terrible. And the art conservator said, well, maybe it doesn't have to really mean anything. It just has to be something that people remember. And something like, she says, I don't know, platypus. I said, platypus. So it's platypus, and we go in the colors between the Duke blue and the green of the University of Brussels, which also worked on this. And you see platypus is learning to climb out of his cradle. And we hope in the future to teach other tricks to platypus. Art conservators are now adopting this. It has been downloaded over 60 times, and soon we actually will make the most updated version available completely for free. So far we were asking people to give us their email address so that we could post them about updates, but we will. It has grown up. We'll leave it completely open. If you look for it, if you look for project-platypus.net, then you'll come out to it. And that's where I'm going to stop for today. Thank you.
Do you have questions?
Did your copies not use any optical devices, like perhaps some of the early painters themselves might have used?
No, she did not. She first of all, and certainly in the 14th century, well, this was not a portrait. This was, I mean, if they used it, it was probably for copying from living scenes, and this probably was not painted from a living scene. But also, it's not clear yet exactly what kind of optical devices they would have used, and so she just did not.
I have two questions. One is the first part of your talk about the murals that were
frescoes.
The pieces of stone are three-dimensional, and you have regions that are actually stone and are not, and the shape of the stone does not conform to the shape of the actual picture. So how do you treat that discrepancy?
Well, it's not stone; it's plaster. I mean, so it's very friable. So the back, it's the front of it. I mean, so the back of it, they just prepared. Are you asking for the reconstruction? Mm-hmm. So they prepared a wall in which they placed the pieces in plaster.
Ah.
I mean, so in order to get that flat surface,
okay.
Yeah.
The second question has to do with the removal of the cradle.
Yes.
Of course, this is applicable to a lot of things.
Mm-hmm.
You knew what you want to remove. So I'm thinking in terms of you have pictures in material science of composite material with
Yep.
various things, and it could be either good or bad. I don't
Mm-hmm.
know from what point of view. What kind of prior knowledge do you need in order to remove features?
In this particular case, we wanted to study the texture of the wood grain in the panel and in the cradle. In some paintings, we will not be able to. It's only when those have different wood grains. In our case, we had mahogany and poplar was the original panel. In the Flemish, in the Altarpiece of Ghent, where there's some pieces that are cradled as well, we will not be able to, because it's a polyptych, and they took them. They took the big boards. They sawed them in two so that they can expose both of them, and so then they were cradled. So there we will not be able to, because they very carefully, in order to minimize possible damage to the painting, sought the same wood sort as. So they used it was on Flemish oak, and those still exist. And so they found old and dry Flemish oak that for the cradle, and so the wood grain is so similar for the two that it's just hopeless to try to remove it. I mean, the horizontal pieces we can because they're against the wood grain, but the vertical pieces we will not be able to. Yes?
Is it possible to think about some kind of formulation that would allow one day to think about reconstructing Palmyra?
About?
Reconstructing Palmyra.
Palmyra. Well, that's a completely different.
There the pieces are three-dimensional.
Yeah, there are actually pieces, algorithms that are used for three-dimensional reconstruction, but again, there will be a lot that is lost again because it's gone away in dust in the explosions. But I'm sure that people will. I know of a group in Heidelberg that has done very interesting thing on 3D reconstruction from pieces for temples in Cambodia. Temples in Cambodia have beautiful decorations on the outside, but inside, prior to the decoration, they're built of, I forget what exactly the name is, it's a funny kind of sandstone that is half eroded, and that when you dig it up off the ground is actually very soft. And you can cut it and easily at that time, and it stiffens up in air, and then it becomes very solid and stone-like. So these stones were used for building the basic construction, and they fit very well in all these temples without any mortar at all. And the theory, they fit in a unique way. The theory is that when they were still soft, they would rub them against each other to make a rubbing, undulated surface that would make them exactly fit one on top of the other. And so when you have all the blocks separated, you know that all those blocks, each of which now weighs several tons and is stone and no longer malleable, will fit in one unique way with all the other stones. But it's not easy to just play puzzle with them. So they're now scanned, and the puzzling is done via optimization 3D programs. And that is then used to reconstruct them in practice. And that's done with UNESCO projects and so on. So not in Angkor Wat, but in more remote sites.
Yes, thank you.